Here we are, kids, at the very end of stoichiometry, questions 16 through 20. This is question 16. We have kind of an unusual balanced chemical equation. Doesn't really fit into our simple five possibilities. So we'll just go with it. In this, the equation starts out with, what if you had 649.6 liters of NO gas form? How many liters of oxygen did you need to start? Now, there's four parts to this. There's ammonia and oxygen and nitrogen monoxide and water. As usual in stoichiometry, we can only look at two parts. So the ammonia and the water they're balanced in this equation, but then we forget about them. This is only about the NO gas and the oxygen gas. So the first thing we have to do, we're going to start out on volume island. We have to get to volume island for oxygen. So this is going to be volume to moles, then mole ratio, and then moles back to the volume to island. So the first step, we're going to turn these liters of NO gas into moles. And to do that, we start out with 649.6 liters of NO gas over 1. And to convert that into moles, we remember that 22.4 liters of any gas is 1 mole. So that's our conversion factor. Since we started with liters in the numerator, we have liters in the denominator here, and we're going to cancel the liters and convert this into moles. And another name for 649.6 liters of gas is exactly 29.00 moles of NO gas. And there's 4 significant figures, so we got to keep those 0 zeros. 29.00 moles of nitrogen monoxide gas. Now, if that's how many moles formed, well, the question is how many liters of oxygen were required. This is a comparison now. We have to go through the mole ratio tunnel. We have to compare moles of NO to moles of oxygen. So we're going to set up the mole ratio. The moles of NO to the moles of O2 from the balanced chemical equation is going to be 4 to 5. 4 moles of nitrogen monoxide gas require 5 moles of oxygen to form. 5 moles of oxygen to be used up. So it's in a 4 to 5 ratio. But we have 29.0 moles of NO gas, so we're going to put that equal to 29 over X, right? 4 to 5 is the ratio. The same proportion has to carry forward, even if it's 29 to X. And when we cross multiply, we get 4X equals, I don't know, 100 and something, 145. And then we have to divide both sides by 4. 4 significant figures. It's going to require 36.25 moles of oxygen in order to make this amount of NO gas. And the question is really how many liters of oxygen are. So we have to convert these moles of oxygen into liters. So we set up a new starting point, 36.25 moles of oxygen. And in order to convert from moles to volume, again, we use the same conversion factor. 22.4 liters is a mole. But in this case, compared to the red one on the top here, look at the conversion factor here. This time the liters goes in the numerator because we start with moles and we have to cancel the moles. So the moles goes on the bottom, liters goes on the top, and then we just have to multiply this out. And with 4 significant figures, the answer is 812 liters of oxygen. Nobody wants to know the answer to this problem. Nobody even cares. I don't even care about the answer to the problem. What this is a challenge. Looking at a balanced chemical equation, do you understand the law of conservation of matter holds that the mass of the reactants equals the mass of the products? From the balanced equation, we know that the moles are in proportion, but nothing else. Atoms are not really in proportion, and grams are not in proportion. Even liters are not really in proportion, but the moles are. And we can make sense of this if we do the math in the proper order, following the map, not getting eaten by the shark. The shark's silly, right? It's a joke. I know it's a joke. You can roll your eyes and be jaded and say, oh, it's a stupid map with a stupid shark. This guy's a pain in the neck. Sure I am. But it's way easier to do it this way than to try to do it by remembering all the steps, just remembering them. Follow the map. You're gonna do fine. Here's another problem. This stuff is called octane. Octane is gasoline. C8H18. That's what you put in a car. The balanced chemical equation is given. It's in a 2 to 25 to 16 to 18 ratio. And it says during this combustion, 125 grams of oxygen are used up. How many grams of water are produced? So this is going to be a grams to grams problem. That's what you have to be able to see here. We're going to start out at Mass Island, and we're going to end up on Mass Island 2. In order to get there, we have to go from mass to moles through the mole ratio tunnel, and then from Moles Island 2 to Mass Island 2. So the first step is to convert these grams of oxygen into moles. So we're going to set it up like this: 125 grams of oxygen over 1. And in order to convert mass into moles, we have to know the molar mass of oxygen. Now, if you put your finger in the box on periodic table, 15.99 something, but that's for one oxygen. Oxygen's a Hunkelbrief. So for O2, it's 32 grams per mole. The grams have to cancel, so the grams go on the bottom. We're going to convert to moles. Moles will be in the numerator. The grams cancel, and this turns out to be 3.91 moles of oxygen. So 125 grams is another name for 3.91 moles of oxygen. So if we use up 3.91 moles of oxygen, how many grams of water are going to form? Well, we have to do now a comparison of moles to moles called the mole ratio. We write mole ratio, and here, I don't know why I put the water on top and the oxygen on the bottom. It doesn't matter what's on top or what's on the bottom, as long as all the water numbers, in this case, will be on the top, and all the oxygen numbers will be on the bottom. Now, the water is an 18 to 25 ratio from the balanced chemical equation, but we don't know how many moles of water. We do know that we're going to have 3.91 moles of oxygen. So see how the oxygen numbers. There's a 25 in the balanced chemical equation for oxygen, and now we have it proportional with 3.91. 25 to 18 is the same as 3.91 is to x. Top and bottom doesn't matter as long as they're consistent. To solve for this, we have to do 25x equals, I don't know, 18 times 3. That's 70.38. And then when we figure the proportion out, cross multiply and divide, exactly 2.82 moles of water are going to form. Now, we have to convert those moles of water into grams, because that's what the question says. Not how many moles, that could be an answer, but it says how many grams. So we take 2.82 moles of water, and we're going to multiply that by the molar mass of water. Now, we've done this many, many times. You write H2O, draw a line, and then under it H and O, and it's 2 times 1 equals 2, and 1 times 16 equals 16. The molar mass of water is 18 grams per mole. You got to remember that. That's a good one to know, so you don't have to do the math all the time. And then we just cancel out the moles, and the answer comes out with 3 significant figures, 50.8 grams of water. Now, this is less obtuse than the first problem. You guys soon are going to be buying gasoline. You're going to drive your car. It's going to combine with oxygen from the air, and it's going to produce the energy to make your car go. You have to be careful and drive safe. Never drink and drive. Always follow the rules. Use your blinker, wear your seatbelt. But look how much carbon dioxide you're going to form. 2 moles of octane is going to produce 16 moles of carbon dioxide gas. That's a pretty big balloon. Every 2 moles of octane you burn, you're going to make 16 moles of carbon dioxide. That's called global warming. Right? The water is fine. Water comes out H2O. It drips on the ground. It comes out as steam. It gets into the air, and then we drink it again. But the CO2, global warming. Got to be careful. Don't drive unless you have to. Okay? Last problem. Oh, I'm a liar. This is 18. This is the next problem, not the last problem. Here we have nitrogen and oxygen going to synthesize into something called dinitrogen pentoxide. The balanced equation 2 to 5 to 2 is perfect. It says here, what if you have 105 grams of nitrogen to react with oxygen? How many molecules of oxygen are required? So in this case, we're starting with grams, or we're starting with a mass of nitrogen. We want to end up with particles or molecules of oxygen. We're not going to worry about the N2O5. It's balanced. It'll take care of itself. It's not in this problem. First step, we're starting on Mass Island. We're going to change 105 grams of nitrogen. We have to convert it into moles. So we have to figure out the molar mass of nitrogen. Now, if you put your finger in box 7, nitrogen's got a molar mass of 14 grams per mole, but that's N. We have N2, so don't forget that. It's 28 grams per mole because it's N2, diatomic Hunkelbrief twin. The grams go in the denominator, so the grams will cancel. The answer comes out in moles. This is division. We get 3 significant figures, 3.75 moles of nitrogen. 105 grams is the same thing as 3.75 moles. Now we have to compare the moles of nitrogen to the moles of oxygen in what we call the mole ratio. We have to get through the tunnel. We have to compare moles of nitrogen to moles of oxygen. Now the moles of nitrogen to oxygen are in a 2:5 ratio. Look at the top, the balanced chemical equation. There's 2 N2s and there's 5 oxygens. That's the 2 in the front and the 5 in the front. 2 moles to 5 moles. But it's a math problem. We don't have 2 moles. We have 3.75 moles of nitrogen. So we put the 3.75 on top divided by x. 2 to 5 is the same as 3.75 is to x. Now we can solve this. It's a proportion. Cross multiply and then divide by 2. And so if we use up 3.75 moles of nitrogen, we're going to need 9.38 moles of oxygen. That's the same proportion. 2 to 5 is equal to 3.75 is to 9.38. But the question here is molecules of oxygen. We have moles. Now we have to do one last conversion. We're going to go from mole island to particle island. And the conversion factor for that is the 1 mole of any gas, one mole of anything is going to be equal to Avogadro's number of particles. So we start over 9.38 moles of oxygen over 1, and we're going to multiply it by Avogadro's number over 1 mole. That's equal to 1. The moles will cancel, and now this is a big problem. To do this, you have to use your calculator. 9.38 times 6.02 equals, then whatever that is, times 10 to the 23rd. You can't forget the gajillions on the end. So that's going to equal in small. It's got to make it really small to fit. 56.4676, that's what your calculator says. You're going to round it to 3 significant figures. So it's 56.5 times 10 to the 23rd. But we have to remember that the coefficient at 56 is too big. It's got to be less than 10. So I make it 10 times smaller, and I make the exponent 10 times bigger. There you go. There you go. All right, there's 2 problems to go. In this problem, again, we have kind of a weird problem. It doesn't fit our simple definition of what kind of reaction is it. It's just kind of a cool chemistry. Nitrogen dioxide and hydrogen gas is going to turn into ammonia and water. Okay, it's an odd reaction. I even wrote that, odd reaction. We're going to use 0.135 moles of hydrogen. And the question there is, in our reaction, 0.135 moles of hydrogen will react to form how many grams of ammonia? Here we're starting in moles and we're going to mass island 2. It's only 2 steps. So wacky as it is, it's actually 1/3 smaller, right? It's only 2 steps. So first thing we got to do, since we're starting with moles, we have to do the mole ratio. That we're going to go from moles of hydrogen, we got to compare that to moles of ammonia. This is a hydrogen to ammonia ratio. The NO2 gas and the H2O, they're not in the problem. They're in the equation, but we only look at 2 things in stoichiometry. So the mole ratio between hydrogen and ammonia is 7 to 2. Make sure you know where these numbers come from. Look up at the top. There's 7 hydrogens, and they're proportional to 2 ammonias. 7 to 2 ratio. But we have some little silly decimal here, so we can't do this in our head. It's not like we're going to double it, right? If it was double the hydrogen 14, it would be 4 moles of ammonia. It would be easy. There's a calculator. It's not hard. You got to calculate it. So we have, instead of 7, we have 0.135 moles of hydrogen, and that's going to be comparable to x. So this could be a really little decimal, but we're going to do the math. 7x equals, I don't know, 0.270, and x is going to equal, with 3 significant figures, a very small number of moles of ammonia. Small, 0.0358 moles. It's not a lot, but that's the question. That's what it is. Now, to answer this, though, we have to figure out how many grams of ammonia. We have that small number of moles. We're going to start over with 0.0358 moles of ammonia over 1. And we have to go from moles to mass island 2. The conversion factor is the molar mass of ammonia. There's another one you could probably remember. There's 1 nitrogen and 3 hydrogens. Nitrogen is 14. Hydrogens are 1 each. It's going to be 17 grams per mole. Since we've got moles in the numerator, we're going to put the moles in the denominator. The moles will cancel, and we got a decimal times 17. Not a big number. 0.609 grams of ammonia. 3 significant figures. This is a 2-step problem. On the island map, we start at mole island, and we want to go to particle island 2. So it's just 2 steps, and there's no shortcut. You can't go from moles to grams of something else. You have to do the mole ratio first. Otherwise, the metaphorical and the real shark, the mole shark, will eat you. All right? Now, this is the last stoichiometry problem besides the homework. Okay? And look what it says in black. This is the hardest stoichiometry problem in the history of stoichiometry problems, but it's also the last one you have to do. We got some crazy, crazy big number of atoms of phosphorus. How many molecules of chlorine gas? Now, this is particles to particles. We're going to have exponents in the beginning, then a mole ratio, then exponents at the end. This, honestly, pain in the neck. This is the messiest, ugliest, dirtiest stoichiometry problem there's going to be, but you can do it. You can do this one. Now, first we have to start with a balanced chemical equation. One phosphorus, right? So far, so good. 2 chlorines, 5 chlorines. That's even and odd. The odd one needs to be doubled, so we have to make a 2PCl5. That means we got to have 2 P's in the front, and we got to have 5 chlorines, and look what we got. Nice balanced equation right here. 2 phosphoruses and 5 chlorines makes 2 phosphorus pentachlorides. Now let's look at the blue on the top. You have some crazy big number of atoms of phosphorus, and they have to react with enough chlorine to make phosphorus pentachloride. How many molecules of chlorine? Well, the first thing we got to do is get off particle island, then we have to convert that giant number of atoms of phosphorus into moles. So 9.42 times 10 to the 29th atoms of phosphorus. To get across the bridge, we have to convert that using Avogadro's number of atoms. So here we go. 1 mole of phosphorus is equal to 6.02 times 10 to the 23rd atoms. The atoms are going to cancel, but we're going to have 2 little problems. We're going to have 9.42 divided by 6.02. Then it's going to be 10 to the 29th divided by 10 to the 23rd. It's going to equal this, and that is going to equal this number. 1.56 times 10 to the 6 moles. 10 to the 6, that's a big number, right? We're going to have, well, that's like we have 6 zeros. It's 156 plus 5 more zeros. We're going to 1.5 million moles. This is crazy. This is a math problem, though. Yeah, it's a lot of phosphorus. Now, mole ratio between phosphorus and chlorine. Phosphorus and chlorine's in a 2 to 5 ratio. Look at the balanced chemical equation there. 2 moles of phosphorus is in proportion to 5 moles of chlorine. We don't have 2 moles of phosphorus. We have 1.5 million or something, some crazy number. So it's going to be proportional to 1.56 over 10 to the 6 moles of phosphorus compared to X. This is going to be a 2 to 5 ratio. The X is going to be even bigger. This is crazy. Crazy, right? Cross multiply, 2X is going to equal 5 times this. 5 times 1.56 is 7.80 times 10 to the 6th. We're going to divide both sides by 2. It's going to equal 3.90 times 10 to the 6th. Uh-oh, looks like we got a little mistake there. I'm going to delete that, and I'm going to turn this into a 2. And I hope that's my only silly mistake, because that means we're going to equal 3.90 times 10 to the 6 moles of chlorine, because it's the mole ratio there, and that's the chlorine. Now we have to take those moles of chlorine and turn them into particles. Let's hope the slides are still going to be good. Oops, I went the wrong way. So we have 3.90 times 10 to the 6 moles of chlorine. Oh, that's good, I fixed it. And now we have to convert that into molecules. So this is a giant number of moles. This is preposterously big moles of chlorine. But to convert it, we just use the conversion factor that 1 mole is Avogadro's number of particles. So 1 mole goes on the bottom. So we have to multiply these gigantic numbers times more gigantic numbers. I don't even know how I'm going to squeeze the answer in here. Let's see what we got. 3.90 times 6.02 times 10 to the 6 times 10 to the 23rd. Now, 10 to the 6 times 10 to the 23rd is 10 to the 29th. We just add them up, right? That's how you do multiplying exponents in your head. You just add up the exponents. So multiply 3.90 times 6.02. That's going to give you 23.5 times 10 to the 29th molecules. But then we have to change that 23.5. It's too big. We have to make it 10 times smaller to make the coefficient less than 10. So it becomes 2.35. And then we make, since we made that part smaller, we make the exponent bigger, becomes 10 to the 30th. This is a preposterous number of molecules of chlorine. This is gigantic, 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 right? A mole is 10 to the 23rd. This is 10 times, 10 times, 10 times, 10 times, 10 times, 10 times bigger. 10 to the 7th bigger than 10 to the 23rd. This is ridiculous, okay? But it's a math problem. Ladies and gentlemen, stand up and take a bow, okay? Stoichiometry is done. You're going to read this. All stoichiometry is math on math. It's mole math with a little bit of ratio in the middle. It is an exercise. You can do this though, right? If you want to do this, right? There's no magic, it's just practice. I have taught stoichiometry. It says 1,200 students, give or take, at Vestal. And most of those students have learned stoichiometry, right? Most of them have forgotten it too, right? Every once in a while I bump into somebody who's from college. They send me an email or they say hi at Wegmans or something. I'm like, hey, remember how to do stoichiometry? I'm like, not really. That's okay, right? You do not have to know how to do this at a moment's notice, right? It's not important, right? You don't have to know it. You don't have to remember how to do it. But right now, this is your challenge. Your challenge is to think and to learn and to work and to make yourself better. It's hard. It's even a little boring, maybe for some of you. I don't understand that, but people have told me that it could be boring, right? You need to practice it to get better at it. Now, you should do these problems over again. You could. How many people are going to do that? Listen to me. I'm giving you suggestions I know you probably won't take. I want you to do the stoichiometry homeworks, all right? I'm going to collect 2 out of 3 of them, and you don't know which ones it's going to be. Probably collect different ones in different classes so that it can torture you. You all have to do all of them, okay? Don't be a baby, and don't let stuff happen to you. Make your life better. It's in your hands. It's a pandemic. It stinks. School's a drag. High school's hard. You're not with me every day. We're not having nearly as much fun as we could. But I'm still your teacher. You're still my student. And I'll do anything I can to help you learn this. It's not about stoichiometry. It's not. What it's about is getting a hard challenge and fighting through it, right? Nothing worth anything is easy. Graduating high school, my goodness, it's harder for you than it's ever been for anybody else, right? But you have to do that. What are your choices? You're going to not graduate high school and you're going to work in a dollar store forever, right? People work in dollar stores. They work very, very hard. There's nothing to be ashamed of, but you could be a school teacher. You could have summers off for your whole life. You know how you do that? You learn stoichiometry. And it's not the stoichiometry, it's fighting through what you have to learn. You have to learn this. Learn this. Call me on the phone. Read my lips. Call me 24 hours a day and ask for help. Don't send stuff in with question marks, right? That's ridiculous. That means it's wrong. That means you gave up. That's the wrong choice. Don't give up. Call me on the phone. I'll help you. I'm bored. What am I doing? I'm freaking shoveling snow. Call me on the phone and I'll help you. All right? Peace, love, and chemistry. Right? We're done with stoichiometry. This is it. Do the homeworks, and we're done with 2020. We put this awful year behind us. Things will be better in 2021. All right? I still love my job. Professionally speaking, I still love you. Think about that.